Hello. I'm going to start now with a description of what happens when one wire is near another wire. I'm going to take the case of, let's say, two wires carrying currents in the same direction, and the wires will be parallel. So let me demonstrate what happens there. And there's two ways you can do it. You can use QV cross B, or you can use IDL cross B. I'm going to hint at both anyways. Here you go. So let's imagine a wire carrying a current upward, I, and then some distance away from that, another wire carrying a current I. I'll call this one number 1, and I'll call this one number 2. I'll try to get that in better focus. Still not that great, is it? There we go. All right, so if you want to figure out what force is on 2 due to 1, I will say the force on number 2 due to number 1 is equal to question mark. So that's sort of the way we label it, is the force on a thing due to a thing. So first off, what I'm going to think about is what about the magnetic field caused by the current carrying wire, number 1. So this is a current carrying wire. It's pointing up that way. I could, in principle, grab it with my right hand, with my thumb pointing in the direction of current, and that tells me the direction my fingers go is the actual direction that the magnetic field points. So what that means is over here, the magnetic field is going into the page, and then of course over here, it's coming out of the page, and then out in front, of course, it's going to the right. So this is the magnetic field due to number 1 at number 2. So this magnetic field on 2 due to 1. Okay, so now that I have that, I can just picture the individual charges going along this wire, wire number 2, and see what magnetic field that magnetic field going into the page would cause. So if I use the equation F equals QV cross B, then I would remember we're talking about positive, our conventional current, so positive charge carriers. I'd say QV is this way. That means I got to keep my hand in some way that my fingers can curl towards B. Again, using the flat hand idea. There's also that idea where you can do like this. I'm going to do the flat hand idea. So I pretend that this pinky is like the axle that makes the wire current too. So I can turn any way like that, but I need to turn away that the magnetic field, my fingers can actually curl towards it. So I have to do it like this so my fingers can curl towards the magnetic field. When I do that, I see the force on the individual charges are acting this way. So I'll say this is the force on wire 2 due to wire 1. So it will point, in fact, that way. Now, let's try with IDL cross B instead. So DF is equal to IDL cross B is another way we could have done it. When I do that, remember I is the direction of the current and DL has to be parallel to it. So you see DL cross B, again, you still get pointing to the left. So what this tells you for starters is that parallel currents are actually attractive. So wire 2 is being pulled towards wire 1 because wire 1 and wire 2 have parallel currents. If they had anti-parallel currents, then my QV would have been this way, and obviously my magnetic field would force me to curl my fingers that way, and that would actually cause a repulsive force. So we've learned something. We've learned that parallel currents attract. And anti-parallel currents, of course, repel one another. Now, what's the actual force? Well, again, if these wires are infinitely long, then we can say that the force on 2 due to 1 is given again by IDL cross B. B is uniform over the whole length. then I just get, it's the magnetic field due to 2 at 1 times current number 2 times length number 2. Okay, so the length of wire 2 times the current going through wire 2, which I just called them both I, but it could have been I1, say, and it could have been I2, say. Now, the magnetic field at 2 due to 1 isn't, or excuse me, on 2 due to 1 is actually B21 equals mu 0 I1 over 2 pi times the distance between them, which I'm going to say is D. So over D, now I can plug that in and I get F21 is equal to mu 0 I1 I2 L2 over 2 pi D. Now, in principle, these wires are infinitely long, so we can sort of get around by talking about what is the force per unit length. So F21 sub L, or excuse me, divided by L2 is the force per unit length. That's mu 0 I1 I2 over 2 pi times the distance between them. That is the force on wire 2 as a result of current in wire 1, namely a current I1. Okay, so that's the force per unit length. So that's one thing we can do. So we can, consider neat things like, what if I have 4 wires, all the currents going up? What direction will the magnetic field point? Right here in the center. So this current right here, this current carrying wire is going to create a magnetic field this way. That's due to that one. This current carrying wire is going to create a magnetic field this way. This current carrying wire is going to create a magnetic field this way. And finally, this current carrying wire is going to create a magnetic field this way, and all of them will be equal in magnitude, so the net force or the net magnetic field in the center is 0. But we can also try trading it up a little bit. What if we say this one's down, this one's up, this one's down, and this one's up? Then we get this one creating a magnetic field this way, dead center. This one's creating a magnetic field this way, dead center. This one is creating a magnetic field this way, dead center. And this one is creating a magnetic field this way, dead center. So in fact, we now get a net magnetic field that just points downward, because these two are at the same angle if it's really in the middle of a square, and they're equal magnitude. So the horizontal component of this one cancels out the horizontal component of this one, and we get a net magnetic field pointing downward. So those are some of the neat types of questions you can answer with just understanding how I dl cross B works, creating another magnetic field. So now if you stuck a current carrying wire in there, you'd say, okay, well, current carrying wire is going to tend to be deflected by I dl cross B. So if I put another wire in there, I now know what direction the B field is. So that makes some sense. That's pretty straightforward. You can also solve problems like if you had a wire horizontal with a current going this way, and you had another current carrying wire going this way, you might say, what kind of current has to go through this top wire in order to counteract the weight in this bottom wire? And you could, actually say this is a fixed current, solve for this current. Those are all neat new tricks, and all it takes is this little equation right here. In this case, you need the mass per unit length of the wire down here at the bottom, and that times gravitational acceleration would be the weight, and you want that to cancel out with this equation. So you just adjust I2 until those two equations were equal in magnitude, and that could do it. So I hope that helps you with those types of problems.